So we're going to be looking at residuals. This is investigation number 2. This is the investigation in front of you. Ideally, we should be using a TI-83 graphing calculator, but since most of us don't have one, we're going to be using Tinkerplots instead. Or, sorry, in this case, we're going to be using Fathom. So what I've done is I've taken this data and I've transferred it into Fathom, and we're not going to follow these instructions to a T, but we're going to do something very similar. So first of all, what we need to do is we're going to create ourselves a table in Fathom with our first and second columns, and then in here I am going to be typing in the data. And here is our data set. So this is the data set from the correlations, residuals, and nonlinear regression investigation number 2. Now, what are we going to do? First of all, we are going to graph this. So I'm going to create myself a graph here in Fathom. Very easy to do. What I need to do is I need to drop an attribute at the bottom. So I'm going to take my L1 and drop it on the x-axis as my independent variable, L2 on my y-axis, my dependent variable. Here is our data set, nicely plotted and nicely graphed. Looks fairly linear. So what we're going to do is we're going to add a least squares line. So down here we also have the formula with an r squared of 85, or 85%, sorry, r squared of decimal 85. So that is the first part of the investigation number 2. The second part is looking at the residuals. So in this case, once again, we're going to use the graph, and we are going to make ourselves a residual plot. I'm just going to extend the graph a little so that we can see it a little better. At the bottom, you can see the residual plot, and you'll notice that most of these data points are pretty close to the 0 line. So there's not a huge amount of variation. This is a fairly decent description of the data, this linear regression. So a nice way that we can summarize what we see here is by saying that linear regression is a very good model for this example because the residuals all hover around the x-axis. The closer the residuals are to the x-axis, the better the fit. So now this is an example of a linear regression with a straight line. The next example, we'll be taking a look at a nonlinear regression, in which case we're going to have to be using a quadratic to describe our data. So now we're continuing with investigation 3, and in this case we're looking at nonlinear correlation. Here we have a data set that graphs year versus the relative cost of something in dollars. And you'll notice that this table is laid out in a non-standard fashion. We've got 6 different columns. Normally we'd only have 2. So I am going to turn this data into Fathom data, which we can then use to look at our results. Now we're in Fathom, and what I've done is I've already entered the data in collection 2. Handy feature of Fathom is that it keeps your data in collections. So I choose collection 2, I go over to table, I drag my table down, and voila, we have the data. So the next step is to turn this into our graph. So once again, I am going to pull my graph down, create a new graph, and I'm gonna overwrite everything. It doesn't really matter if we can see those. And once again, our year is going to be our x attribute, and the relative cost is going to be the y attribute. So in this case, it looks pretty obvious to the untrained eye. We have a curve of best fit. So let's see whether that holds true. So I am going to add our least squares line, and you'll notice that this is a linear regression rather than a nonlinear regression. And even here we get an r squared of 0.89. So on the face of this seems like a pretty solid linear regression. And with an r squared of 0.89, you would think so, wouldn't you? So let's go the next step and add our residuals. And you'll notice, compared to the other collection, where it was very definitely a linear regression, you'll notice how on the left we have all of our residuals clustering fairly close to the x-axis. When we look at the residuals for the graph on the right, you'll notice that there's a very distinct pattern, and even in the absence of a distinct pattern, these residuals are not clustering around the x-axis. So this is definitely not a data set that is properly described by a linear regression. So we're going to have to try something else, and that something else is going to involve Microsoft Excel because Fathom cannot do quadratics. Here we're in Microsoft Excel. I have selected my two data columns. I am going to insert a scatter plot. Just going to make it a little bigger, and the other thing I'm going to do is right-click on my data series and add a trend line. That trend line in this case is going to be a polynomial, because I'm going to look at a quadratic. I'm going to be doing a second order polynomial, so that's ax squared plus bx plus c. And I am going to ask to see the equation on the chart, and I'm going to ask for the r squared value on the chart. So here is my nice little graph, and you can see that the trend line, or in this case the trend curve, fits very nicely with the data. We also have a very nice r squared of 0.995, so 99.5% of the variation in the one variable is explained by the other variable. That's a very nice correlation. Unfortunately, I cannot quickly show you the residuals, but you can see just looking at this that the residuals here would be very small compared to the residuals that you saw in Fathom. So remember, here in Fathom, you can see those residuals are quite distinct. Here you would have long ones, and actually, come to think of it, I can display them nicely. In Fathom, I can show the squares, which in effect is a display of the residuals. So you can see that the residuals are getting quite large at the bottom of the graph, in the middle of the graph, and at the top of the graph. There is a distinct pattern to how the residuals are shown here. In this case, you can see that the residuals, the ones that are there, are very, very small. So that, in a nutshell, ladies and gentlemen, is our examination of nonlinear and linear correlation. Our three investigations are covered by these two YouTube videos. I encourage you to check out the other YouTube video as well. So let's just finish off with a quick summary of investigation 3. In this case, I would say that the quadratic model is a good fit for this data. And one thing that I just noticed, this data represents the relative cost of going to school, to post-secondary institution. So in 1975, the relative cost was $30 per whatever. In 2000, the relative cost was $200 per whatever. So that's a nearly 8-fold increase in the cost of going to school. So if this were to continue like that, do you think it would be affordable for you to go to school in the near future, especially if you postponed going to school?